Okay, so we have Setiawan from Riverlane that is going to talk about tailoring dynamical code for bias noise in the X3Z3 Floquet code.
Thank you for the introductions. I'm Setiawan from Riverlane, a company focusing on quantum error corrections. So today I'm going to present a new kind of locate code that has improved performance under bias noise. So to begin with, let me go through with you about the basics of locate codes. Locate codes are dynamical codes where the logical qubits arise from periodic schedule of anti-commuting measurements. So compared to stabilizer codes, for example, surface code, it has several advantages. For example, it has lower weight checks. The syndrome measurement can be done without ancillar qubits, and it has better threshold and sub-threshold performance for certain noise model. So while locate codes have been studied quite extensively, most studies focus on its performance under depolarizing noise. However, in most platforms, the noise is biased, which means that a certain type of error, for example, phase error, occurs more frequently than the other type of error, for example, bit flip errors. So the question here is, how can we tailor the locate codes for improved performance under biased noise? Before I go into the details, let me go through with you the basics of locate codes. So in this talk, I focus on locate codes which are defined on 2D lattices with qubits sit on the vertices. Specifically, I will consider a trivalent and three-colorable lattice, for example, the honeycomb lattice. And here, each edge and plaquettes are assigned one of the three colors, red, green, or blue. And the plaquettes are colored in such a way that there are no two adjacent plaquettes of the same color, which means that the red plaquette here can only be next to green or blue plaquettes and cannot be next to the other red plaquettes. And each edge is assigned the same color as the plaquettes that it connects. We perform error corrections by measuring the edge operators or checks in particular sequence, for example, the red, green, blue sequence here, and repeat. And the basis of the checks are chosen in such a way that consecutive edge operators anti-commute. And from these check measurements, we can infer the values of the plaquette stabilizers. The most popular locate codes are the CSS locate codes, color codes, and honeycomb codes. So in CSS locate codes, regardless of the color, each edge can be assigned XS and ZZ operator. So we have in total 6 different kind of edges, and we measure in a period of 6. So we use the red, green, blue sequence, but alternate between measuring XX and ZZ operators. While in honeycomb codes, each edge is only assigned one kind of operator, either XX, YY, or ZZ operator, and we measure in a period of 3. The other difference is that in CSS locate code, we infer the value of the plaquette stabilizers from the check measurements in one time step, while in honeycomb code, we need 2 time steps. So the last difference is that in CSS locate codes, we have 6 different plaquettes, each of which has one of the 3 colors and is either all X or all Z. And however, only 5 of these plaquettes belong to the instantaneous stabilizer group at any one time, because the other one anti-commute with the check measurement at that time. And these inactive plaquettes will be reinitialized at the next time step and later measured out. So for this CSS locate codes, there's no constant instantaneous stabilizer group. While on the other hand, for the honeycomb codes, we have 3 different plaquettes, and all of them belong to the instantaneous stabilizer group. And there are 2 variants of honeycomb code. The first variant here has the same operator XYZ operator for all the plaquettes, and hence I will call it XYZ square plaquette, XYZ square honeycomb code. While the second one here is related to the first one by single cubic Clifford rotations, and has all the plaquettes either of all X type, all Y type, or all Z type, depending on its color. And I will call this P6 honeycomb codes. Our bias-tailored X3Z3 codes is a floccatified version of the domain wall color code, or it can also be thought of as Clifford deformed CSS floccate code, where we apply Hadamard gates on half of the data qubits, which are the data qubits on the sharded domains. This transformation changes the H and plaquettes from the X and Z types to A and B types, where A and B types plaquettes have 3X Paulis and 3Z Paulis, hence the name X3Z3 flockade codes. And despite not having constant instantaneous stabilizer group as in CSS flockade code, there do exist operators in these X3Z3 flockade codes which forms a persistent symmetry under pure defacing noise. So these symmetries are formed by the product of plaquette operators of a single type along vertical strips in the lattice at time t, which commits with the check measurement at the next time step t+1. So an example symmetry just before the green B check measurement is shown here. So the symmetries here is a product of red and blue A-type plaquette along the unshaded domain. Since the product of these plaquettes is equal to identity along this unshaded vertical strip, it means that Pauli Z errors will create pairs of anions or flipped pairs of detectors along these vertical strips. And similarly, there also exists similar symmetry for type B plaquettes. And these symmetries will give rise to simplified decoding problem for the X3Z3 code, where the decoding graph under the pure Pauli Z noise model without any measurement error decomposes into collection of 2D planar subgraphs on the vertical strips which are disjoint from each other. And here, as you can see here, since we have the 2D graphs for the pure defacing noise, we can have a simple decoding problem, and hence they will lead to a better performance compared to other flockade codes. And to prove that our X3Z3 flockade code is most likely the most optimal flockade codes, bias-tailored flockade codes, we proved two theorems that show that for a general dynamical code which is built from 2-qubit parity check measurements, the decoding problem cannot be simplified further to 1D decoding graphs as in bias-tailored static codes like XZZX code or domain wall color code. So this is because in static code, only measurements can produce time-lag edges, while in flockade codes, even Pauli errors can give rise to time-lag edges. And we study the code performance under two different noise models. The first one is code capacity noise model, where we apply single qubit errors to the data qubits at every time step, but the measurement resets and gates are assumed to be noiseless. The second noise model is an entangling measurement noise model, where we assume, which may make the hardwares with native direct parity check measurements. Here we assume noisy multi-product Pauli gates, noisy reset and measurements. We simulate X and Z memory experiment and compute the combined logical error probability from these two experiments. The simulations are done by varying noise bias strength from depolarizing to defacing, and to generate the stabilizer circuit, we use STEAM, and we decode the error syndrome using a minimum weight perfect matching decoder. And here is the results. So we compare the performance of 4 different flockade codes, X3Z3 CSS, and 2 variants of honeycomb codes, XYZ square and P6 honeycomb codes. As you can see here from the curve, the blue curve, X3Z3 outperform all other codes at all bias, where the threshold increases with noise bias. Under the capacity noise bias model, it increases from 1.13% to 3.09%, and under the entangling noise measurement noise model, the threshold increases from 0.76% to 1.08%. So to maintain high performance implementation of our code in hardwares without native parity check measurements, we also propose bias preserving parity check circuits. So our circuits can maintain the Z noise bias even when the error happens during the 2-qubit gates. So to preserve this kind of noise bias due to the mid-gate errors normally requires the use of bias preserving 2-qubit gates, which are only available for certain hardwares, for example, cat qubits. The nice thing about our circuit is that it is built from conventional 2-qubit gates, therefore can be implemented in a lot of quantum platforms. So here's the conclusion. So I have presented the X3Z3 flockade code, which has improved performance under bias noise, and we also show that it has simplified 2D decodings, and it cannot decode the graph for general flow-gate code cannot be reduced further to 1D graph. Therefore, the X3Z2 code is most likely the most optimal flow-gate codes. And we also presented the bias preserving parity check circuits. And that's all for my talk. Thanks for your attention.
So we have time for question. I actually have a question for your circuit implementation. Did you try to check compared to the surface code implementation with a realistic gate noise model, how it compare? Because this is one of the problems of the honeycomb code, is that with realistic gate noise, it doesn't perform that well.
Yeah, so here we assume a circuit level noise model, but the circuit level noise model is only for hardware with native parity check measurements. Yes. So we have not simulated the circuit level noise model where you don't have that native parity check measurement. Yes.
Okay. Thanks for the nice talk. This is interesting. So your no-go theorem about like, oh, you can't have a repetition code decoding graph for Z-bias noise, is this a consequence of the flow-gate code being like a space-time code? And so any space-time code that you write down, regardless if it's honeycomb, do you think this is going to be the case?
Yeah, I would say our theorem is only for general dynamical qubits codes which are built from 2-qubit parity checks. So we have not proved it in general.
Okay.
Yes. So this is only for that specific dynamical codes.
I see. Thank you.
Yeah.
Let's thank the talker once again.
Yeah. Thank you.
Thank you.